Okay, so I want to start with something that happened to me. I'm watching a video about word embeddings. Honestly, one of the best on the topic, something like 330,000 views. And around minute 8, the author is drawing the network. 10,000 words in, then a hidden layer, much smaller, let's say 300. And then the author moves on, which is fair enough. You can't stop for every number. But I'm sitting there going, wait, why 300? Who picked 300? Now, it's not just me. You scroll the comments under that exact video and people are asking that exact question year after year. And nobody answers. And that's nobody's fault. The video is recorded, it's frozen. And a bit later, the author opens a notebook and runs the numbers. Distance from dog to cat, 0.239. Nearest neighbors of cat, 10 lines of text. Which is genuinely useful, but it's text. I don't want to read the map, I kind of want to see it. So, okay, you go ask a model instead. And here the usual objection kicks in, and it's a fair one. An LLM answers with text, a wall of text. Well, not anymore. There's this small library called rough.js, and it draws boxes and arrows and circles that look sketched by hand. It's the engine behind Excalidraw. So we invent nothing here. We hand rough.js to the model and say, draw with this. And by the way, everything you're looking at right now is drawn with rough.js. And here's what you get. A model drew these frames for this video. That's a real embedding matrix with a row being pulled out. That's a matrix times a vector, every single product on screen. And that's the error running backwards through all 82 numbers. Every number there is a real computation. Now, I don't want to oversell this. The first draft was honestly kind of a mess, and I'll stop the film a few times to show you where it went wrong. So here's the experiment. I took those same embeddings and asked a model to explain them from scratch. Visuals only, and movies instead of words, so the example isn't the worn-out one. And how to picture that is the model's call too. It wrote 10 analogies, ran them side by side, and the winner was a city of movies, where every film is a point on a map. And on the way, we hit everything that flew past us at minute 8. Okay, let's see how it works. Okay, so let me set the stage. Picture an online movie service. Every time a user finishes a film, one new row gets appended to the watch log. And that row has just 3 fields: who watched, what they watched, and what rating they gave. A whole number from 1 to 5. The rows arrive in time order, so for any user we can read off the complete chain of their views, from first to last. Now here's user 17, and here are his 3 most recent rows. The Matrix, rated 5. Terminator, rated 4. Titanic, rated 2. And here's the task we're going to be working on for this entire film. Looking at just these 3 rows, nothing else, predict which movie this person will watch next. Now you might reasonably ask, why exactly the 3 most recent views? And the honest answer is, that's a developer's choice, a trade-off. One film is too little. From a single view, you really can't tell a stable taste from a random click. And the full history has the opposite problem. Everyone's is a different length. One person has 5 views, another has 5,000. And the construction we're about to build is going to demand an input of the same size for everyone. Why? You'll see the moment we actually assemble that input. Hold on to that question. So 3 recent views is a compromise. A small, fixed slice of history that already tells you where the interest is heading right now. One more setup decision. I want every computation in this film to be visible in full, down to the last digit. So we're going to work with a tiny catalog of 6 films: The Matrix, Terminator, Alien, Titanic, Notting Hill, The Mask. A real movie service has tens of thousands. And at the very end, we'll come back to real scale, and you'll see that nothing about the construction changes. Only the sizes do. So for now, 6 cards on a shelf, a log with 3 rows, and a question: what comes next? But before we build anything, there's a question worth asking honestly. What does predict even mean here? Can a person's choice really be computed at all? So can you guess with certainty? No. A person can choose anything, and there's a lot of randomness in the choice. But, and this is the important part, the choice isn't entirely random either. Someone who just enjoyed 2 sci-fi action movies is more likely to continue with sci-fi than with a costume romance. And the log holds millions of little regularities like this. That's a verifiable fact, and it's exactly the thing that makes this task solvable at all. So the reasonable goal is not name the one correct film. The reasonable goal is estimate the chances of every film in the catalog to be the next one. For our catalog, that's 6 numbers, 1 per film. Alien will presumably get a large chance, Notting Hill a small one. And if we need a single prediction, we just take the film with the highest chance. If the service shows a whole shelf, take the several films with the highest chances. One thing to notice, we're predicting only which film, not what rating he'll give it. That's just how the task is posed. Predicting the rating is a separate task for a separate construction. Okay, so we need a device that takes 3 rows of the log and outputs 6 chance numbers. Now, the most natural first impulse is to skip devices entirely. Just count in the log what tends to follow which triples. Honestly, that's what I'd try first. So let's actually try it and watch where it breaks. Here's the plan. We set up a giant table. A row of the table is a triple of films, and in that row, we count straight from the log After this triple, Alien was watched so many times, The Mask so many times, and so on. And the shares of those counts are ready-made chances. After our triple, there are 9 continuations. Alien 7 times, The Mask twice. So 7/9 for Alien, 2/9 for The Mask. No math harder than counting. Looks great, right? Now let's count what this costs. For 6 films, the number of possible triples is 6 by 6 by 6, 216. Already a lot, but fine. Now the real catalog, 10,000 films. 10,000 cubed is a 1 with 12 zeros, a trillion triples. And even if the log holds a billion views, a gigantic log will have seen fewer than 1 triple in 1,000. So almost every row of this table just stays empty. A user shows up with a triple the log has never seen, and the table has literally nothing to say. It's silent. And it's actually worse than that. The table can't share experience between rows. The Matrix, Terminator, Titanic, and Terminator, the Matrix, Titanic are different rows, and everything we learned about the first one does nothing. Nothing at all for the second. And notice, we haven't even brought ratings into this. Add ratings to the table row, and you multiply the number of rows by hundreds. So let me land the real point here, because this is the reason everything ahead exists. The data will always be vanishingly small compared to the number of possible histories. Always. What we need is a way to transfer experience. What we learn on some triples has to help us answer on other similar ones. And this idea has authors and a history, and it's worth telling properly. So it turns out language researchers hit exactly this same wall. Their task sounds almost comically similar to ours. Given the last few words, predict the next word. And at first they solved it exactly the same way, with tables. For every pair or triple of words, count in huge bodies of text what comes next. A vocabulary of 17,000 words gives you the same trillions of triples, and almost any phrase you're reading right now never once appeared in those tables. Same wall, same silence. In the early 2000s, Yoshua Bengio and his colleagues proposed a way out. And this idea today underlies both recommender systems and large language models, so it's worth slowing down for. It has 2 parts. Part 1, assign every word a short vector of numbers, and crucially, not chosen by a human, but fitted automatically from data. Part 2, compute the chances of continuations not from a table, but with a tunable function that takes the vectors of the recent words as input. And this is the key point, so let me say it separately. You fit the vectors and tune the function together with one shared mechanism so that the predictions match what actually occurs in the texts. Why does this cure the table's disease? Here's the intuition. If the vectors for cat and dog come out similar, and we'll see later why training makes them similar all on its own, then a function trained on the cat walks on will give a sensible continuation for the dog runs on, a phrase it has never seen. The experience transfers through the similarity of the vectors. This property has a name, generalization, and it is exactly the thing the table never had. And our task has the same shape. Films instead of words, views instead of phrases. So here's the plan for the rest of the film. Figure out what these vectors are, how the function over them works, and how both get tuned from the log. Let's start with the device itself, the thing we'll be tuning. The device we're going to build is called a model. That's the machine learning term, and the word sounds grand, but what it names is something simple, a function. It takes an input, 3 film numbers and 3 ratings, runs a predefined chain of operations on it, and produces an output, 6 chance numbers. And I want to reassure you up front, the whole chain will consist of operations you already know. Multiplying a matrix by a vector, adding vectors, applying simple functions to individual numbers, that's it. Now inside this function live numbers of a special kind, and they're called parameters. Parameters are not input data. Every user has their own input, but the parameters are the same for everyone. They are the internal settings of the function itself. The picture I'd keep in mind, a box with knobs. The box processes whatever you feed it, but how it processes depends on where the knobs are set. And here is the central promise of the whole construction. Nobody will ever set those knob values by hand. An automatic procedure will fit them from the log so that the predictions match real continuations. That procedure is called training, and a whole part of this film is devoted to it. Until we get there, we're going to honestly build the function itself, and every time a new number shows up, we'll ask the same question. Is this an input? Is this a parameter? Or is this a number the developer chose once and for all? Keep that 3-way question handy. We'll use it a lot. And the very first step already forces it. The input contains film numbers. Can you feed a number into an arithmetic function, just as a number? So a film got its number in the order it was added to the catalog, which means it's a label, like an inventory tag in a warehouse, a name that happens to be written in digits. But our model is an arithmetic function. Whatever gets inside will be multiplied, added, compared by size. So let's actually check what arithmetic does with these numbers. Titanic is number 4, Terminator is number 2. 4 is twice 2, so Titanic is twice Terminator? That's nonsense. Notting Hill minus Titanic equals The Matrix? Nonsense. The average of The Matrix and Alien is Terminator? Nonsense again. And here's the annoying part. Those three films really are similar. But they're similar not because their numbers happen to sit next to each other. They could have been added to the catalog in any order at all. So, the size of the number means nothing. The difference of the numbers means nothing. And yet the model will inevitably use both size and differences. It can't do anything else. Inside, it has only multiplication and addition. Feed the number in as a number, and you are laying false claims right into the foundation. Claims about which films are bigger and which are closer. The model would trust them because arithmetic is all it has. What we need is a representation where arithmetic tells the truth. And we'll do it in 2 moves. First, build one that at least doesn't lie, and then see what it's still missing. Okay, so here's the simplest honest representation. To film number I, we assign a vector of length 6, the length of the catalog. A 1 at position I, zeros everywhere else. The Matrix, a 1 in the first position. Terminator, a 1 in the second, and so on. This kind of vector is called one hot. Exactly one position is lit up. And notice, the false size is gone. All 6 vectors are built exactly the same way. None of them is bigger than another. Now let's check for false similarities too, and for that we'll use the dot product. Quick reminder of what that is. The dot product of 2 vectors of the same length is the sum of pairwise products of the numbers standing in matching positions. It comes out large when the big numbers of one vector line up with the big numbers of the other, which makes it a natural measure of how well 2 vectors agree. We're going to be using it constantly, so it's worth getting comfortable with now. Let's try it. The matrix.terminator. The ones sit in different positions, so every pair of factors has at least one 0 in it. The total is 0. The Matrix and Titanic, 0 again. And you can see the pattern. Any 2 different films give 0. All pairs are equally dissimilar. So no false similarities, but no true ones either. And similarity was the entire point. Transferring experience, generalization, all of it rests on Alien being represented similarly to the Matrix and differently from Titanic. One hot simply has no way to express that. In one hot, every film is its own island, and all the islands are exactly the same distance apart. On top of that, it's wasteful. In a real catalog, this is a vector of 10,000 numbers, of which 9,999 are zeros. So, honesty we've got. Now we need to add the thing that actually matters. Similar films should get similar representations. And for that, we're going to change the point of view entirely. Stop handing films labels and give every film a place. Okay, quick pause before the next scene, because this is where I made my favorite request. The model was about to introduce embeddings the standard way. Each movie becomes a vector of numbers. Here it is, 2 numbers. Technically correct, and completely dead. You look at 0.9 and 0.8 and you feel nothing. So the request was, don't print the vector, draw the place where the movie lives. Because if 2 numbers are coordinates, then somewhere there's a map. And that single sentence turned into the whole city metaphor. Watch the next scene. The row of numbers becomes a point you can actually look at, and similar starts to mean nearby. So here's the picture I want you to hold on to for the rest of this film. Imagine all the films of the catalog as points in one shared movie city. Every film has its own place on the map, written as coordinates, in our teaching example, 2 numbers. And the film's vector of coordinates is called its embedding. The word means exactly what it says, a placing into. The whole catalog gets embedded into one shared space, and every film becomes a point in it. Embedding, a point on the map. Same thing, and I'll use both names interchangeably. Let's look at the map. And I should be upfront, I'm jumping ahead here. What you're seeing is a snapshot of the map of an already trained model, and where these particular numbers came from is something we will work out in full detail, I promise. The Matrix is the point 0.9, 0.8. Terminator, 1.0, 0.6. Alien, 0.8, 1.0. Notice, all the sci-fi packed together in the upper right corner. Titanic, minus 0.8, 0.9, and Notting Hill, minus 0.9, 0.7, have their own district over on the left, and The Mask, 0.1, minus 0.9, stands apart at the bottom. Now feel the difference from one hot. There, the representation could say exactly one thing about 2 films. Different. Here it says incomparably more. Alien stands next to The Matrix and far from Titanic. Similarity is expressed literally, by placement. And that is exactly the property this whole detour was for. If the model function works with coordinates, it will treat two neighboring points similarly. So experience accumulated on the matrix will spread to alien on its own. One thing I want to settle once and for all, so the imagery never gets ahead of us. The map, the points, the city, these are names for real mathematical objects, not new entities. A point is a vector of two numbers. The map is the set of all such vectors. And every image we introduce from here on will arrive the same way. A name, and immediately the vector or the matrix standing behind it. But notice, one word slipped by just now without a definition: next to. On a city map, near is measured in kilometers. What about on ours? The distance between 2 points of our map is computed exactly the way you learned in school geometry. Take the difference vector and compute its length, the square root of the sum of the squared coordinates. That's all it is, the Pythagorean theorem written for vectors. Let's check it against our snapshot. The matrix, 0.9, 0.8, and alien, 0.8, 1.0. The difference is 0.1 minus 0.2. The length is the root of 0.01 plus 0.04, roughly 0.22. Neighbours. Now the matrix in Titanic, minus 0.8, 0.9. The difference is 1.7 minus 0.1. The length is about 1.7, the other end of town. 3 clarifications so the map doesn't quietly deceive us. First, coordinates can be any real numbers. Negative ones are exactly as legitimate as positive. The map has no edges. Second, the origin, the point 00, is a conventional mark, like a city's kilometer zero. It carries no meaning of its own. Third, and this is the important one, nobody labeled these axes, and they have no units. The meaning is carried not by the coordinate values themselves, but by the mutual arrangement of the points, what sits near what, and in which direction. You could shift the whole city a meter to the right and nothing would change. So now we have a language. Films are points, similarity is small distance. What's left is housekeeping. Where do the coordinates of all the films actually live, and how does the model fetch them? Let's collect the coordinates of all the films into one table. Call it the city's atlas. Formally, it's a matrix E of size 6 by 2. 6 rows, 1 per film, 2 columns, 1 per coordinate. Row number 4 holds Titanic's coordinates, minus 0.8, 0.9. In a real movie service, this atlas would be 10,000 by 64, but it's still just this same table, only bigger. Now, the single most important fact about this matrix, every one of its cells is a parameter of the model, one of those tunable numbers from the box with knobs. Training will change them, and changing the numbers in E means moving points across the map. I want you to remember this identity, because we'll lean on it constantly. Training embeddings and moving points are one and the same thing. So how does the model fetch coordinates? By the film's number, it takes the corresponding row of E. This operation is called lookup, take by index. And it sounds like something external to arithmetic, like a little database operation bolted on. But watch this. Here's a careful observation. Multiply Titanic's one hot row vector, 0, 0, 0, 1, 0, 0, by the matrix E. By the rule of vector times matrix multiplication, each column of E gets folded with this row, and from each column exactly its fourth element survives. The result is precisely the fourth row, Titanic's coordinates. And the shapes agree. 1 by 6 times 6 by 2 gives 1 by 2. Now in practice, nobody actually runs 6 multiplications just to grab a row. You take it directly. But the equivalence matters in substance. Going from a number to coordinates is a linear operation on the honest one-hot representation, which means the embedding is built into the model's overall matrix chain, and the single tuning mechanism we'll build later will tune it too. No separate coordinate trainer required. At this point, we've quietly accepted 2 numbers without any discussion. Why exactly 2 coordinates, and where the values in the cells of E came from in the first place? Let's take them in order. So why 2 coordinates? Because we chose that number, before any training. Numbers like this are called hyperparameters as opposed to parameters. Parameters get tuned automatically. Hyperparameters get set by the developer. So in our atlas, the cells of E are parameters. The number of columns in E is a hyperparameter. Same table, 2 very different kinds of numbers. And the logic of the choice is a trade-off. Let me walk both sides of it. With one axis, the points are cramped. Try lining up sci-fi, romances, and comedy on a single line so that everything dissimilar stays far apart. You'll already be stuck on the mask. Between which districts do you even put it? Every new axis is an independent direction the points can spread out along. So why not lots of axes? Well, more axes means more numbers in E, so memory and compute get costlier. But the deeper problem is this. On a very spacious map, every film has room to claim its own far-off corner, and the map has no reason to group similar things together. And grouping is exactly what we need. The whole transfer of experience rests on it. Besides, to fill a big space meaningfully, you need incomparably more data. Real systems land somewhere in the dozens or hundreds of axes. 32, 64, 256. In our teaching example, we take 2, for one reason only. So the map can literally be drawn and every computation shown in full. And none of the formulas ahead depend on this choice. The vectors simply get longer. So much for how many columns. The second postponed question is still sitting there. What is written in the cells of E at the very first moment, before training has taken a single step? At the very first moment, the cells of E are filled with small random numbers, say from the range -0.05 to +0.05. And here's what our starting map looks like. All 6 points huddled in a tiny blob near the origin, completely mixed up. Titanic pressed right against the matrix, alien next to Notting Hill. There is no meaning in this arrangement whatsoever. And honestly, that's fair. There's nowhere for meaning to have come from yet. Now, why random? Why not, say, all zeros? Here's the thing. If all the rows of E coincided, all the films would sit at one point and be indistinguishable to the model. Whatever the user watched, the same input would arrive. And it's worse than that. We'll see later that the corrections training hands the numbers are computed from the numbers themselves. So coinciding rows would receive coinciding corrections and stay glued together forever. The random scatter is individuality, something for training to grab onto. And why small? Because the starting coordinates are a seed, not knowledge, and a seed shouldn't shout. If one point happened to start 1,000 units away from the rest, it would drown out every sum it entered by sheer size, and the first steps of tuning would come out sweeping and unstable. The exact boundary of the range is not sacred, by the way. Hundredths, 300ths, a tenth, they all work about the same. What matters is the order of magnitude. So let's fix, explicitly, the promise that training will have to keep. Out of this gray cloud must come that blue map from the embedding scene. Sci-fi clustered, romances clustered, and nobody ever telling the model a single genre. Hold that promise in mind. The whole training part of this film is the story of how it gets kept. Meanwhile, back to user 17. We've learned to represent films. But his log holds more numbers than that, the ratings. So, does a rating need an embedding too? No, and the reason why not is actually instructive. The film number needed an embedding because the number is a label. Its size lies. But a rating is not a label, it's a genuine quantity. 5 really is more than 3, and the difference of 2 ratings really means something, how much more they liked it. With numbers like that, arithmetic tells the truth. So they can go into the model as they are. As they are, but with one small cosmetic operation called normalization. Subtract 3 from the rating and divide by 2. So, 1 turns into -1, 2 into -0.5, 3 into 0, 4 into +0.5, 5 into +1. Why subtract 3? So that the middle of the scale, no feelings either way, becomes 0, and liked it and didn't like it get opposite signs. Remember, the model adds and multiplies. Opposite signs are a built-in way to add the good and subtract the bad with one and the same mechanism. And here's what happens if you skip this. Say you just divide by 5. All ratings stay positive. Strongly disliked looks like liked but weakly. And the model has to learn the very idea of displeasure by some roundabout path. And why divide by 2? To squeeze the rating into the range from -1 to 1, comparable with the point's coordinates. And those, remember, start out as hundredths. Put raw 5s next to hundredths, and the ratings shout loudest in every sum they enter. Training would first have to spend a long while just quieting them down. In the maps language, I like to think of ratings as flags planted on the visited points. For user 17, the matrix carries a flag of +1. It was great here. Terminator, +0.5. Titanic, -0.5. Don't come back. A flag is simply a number, call it R tilde, 1 per visited point, nothing more. So now we have 3 points and 3 flags, 6 pieces of input. But the model takes 1 input. Time to glue everything into a single vector. Here's the gluing. Take the three embeddings in viewing order, from the earliest of the three to the freshest, and write them out one after another. The coordinates of the matrix, then terminators, then Titanics. After them, append the three flags, +1, +0.5, -0.5. This operation is called concatenation, literally gluing, and the result is a vector of 9 numbers: 0.9, 0.8, 1.0, 0.6, -0.8, 0.9, 1, 0.5, -0.5. Let's call this the root sheet, and as always with our imagery, it's only a name. Mathematically, it's an ordinary vector x of 9 numbers, a complete description of the recent root, the coordinates of the 3 visited points, and the flags on them. Now, one thing about this vector matters a lot. The positions in it are fixed once and for all, the same for every user. The first and second cells are always the coordinates of the earliest film of the triple. The fifth and sixth, always the freshest. The seventh is always the first film's flag, the ninth, the third's. Notice there's no little sign inside the vector saying, the third film lives here. The correspondence rests entirely on the constancy of the convention. And that turns out to be enough. The next stage of the construction, as we'll see, keeps a separate tunable coefficient for each of the 9 positions, so it can treat the fresh film differently from the old one, and it can tie each flag to its film. Now, why gluing? Why not something shorter, say just sum the 3 embeddings? Because gluing loses nothing, and the sum loses irreversibly. Once you add the coordinates up, you can no longer recover who came first or whose flag was whose. And you can check that on our actual numbers. The sum of our 3 points is 1.1 and 2.3. 1 point instead of 3, and from it you can't see the order, and you can't see that Titanic came with a minus. 2 closing notes. First, here the promise from the very first scene gets kept, the why 3 films and not the whole history question. The gluing has rigidly fixed positions. The input must be the same size for every user, and histories all have different lengths. The triple is what makes the input uniform. Second, films in the triple can repeat. Someone rewatched a favorite. Nothing breaks. The same row of the atlas is taken twice and goes into both of its slots. So the root sheet is ready, 9 numbers. Next, the model has to squeeze the essentials out of them. Figure out from the root where the user is now, that is, what he wants right now. And this is where things get really interesting. 3 points and 3 flags are not yet an answer to what does this user want now. They're raw material. What we need is a summary, one compact digest of the root that the next stage can use to judge the candidates. And let's try to get that summary in the simplest way vectors offer, averaging. Genuinely, this is the natural first move. Let's make it and see. Add the 3 visited points, divide by 3. We get the point 0.37, 0.77. Somewhere between the sci-fi and the romances, slightly right of center. And honestly, it looks reasonable. The root's center of gravity. Now an experiment. Take a twin user, same 3 films, but he didn't suffer through Titanic with a 2. He adores it, rating 5. His taste pulls left toward the romances. Our hero's taste pulls right, away from them. Opposite people. Let's recompute the average. Except, there's nothing to recompute. The flags don't appear in the averaging formula at all. Same point, 0.37, 0.77. 2 opposite tastes, 1 summary. That's a failure. And a second, smaller experiment, shuffle the films. Say Titanic was not the last of the 3, but the first. The average is the same again, because addition doesn't remember the order of its terms. And order is information. A fresh view says more about the current mood than an old one does. So the diagnosis is precise. The summary must account for the flags and for the positions, and the average by construction sees neither. Now the first urge is to patch the formula by hand. Fine, let's weight the points by the ratings. Let's try exactly that. There's a more important lesson waiting on that road. So weight the points by their flags. Multiply the matrix by +1, Terminator by +0.5, Titanic by -0.5, and add. We get the point 1.8, 0.65. And this is genuinely better. The beloved matrix pulls the summary toward itself at full strength, and Titanic, with its minus sign, pushes the summary away. The flags are working now. But look closer because there are cracks. Flaw 1. A film rated 3 gets a multiplier of 0, and vanishes from the root without a trace, as if it were never watched. But watched it and felt nothing is information, not emptiness. Flaw 2. Order is still ignored. The terms are all equals in a sum. Sure, we could keep tinkering. Give the fresh film a bigger multiplier. Okay, how much bigger? Twice? 1.5 times? And then flaw 3, the one that actually matters. Where did we even get the idea that the right move is to multiply the coordinates by the flag? Maybe a bad rating shouldn't reflect the point. Maybe it should just switch it off. We don't know. And the honest answer is, nobody knows. The right way to summarize a root isn't written in any textbook. It hides in the data, in millions of real continuations. And at this point, recall Bengio's idea in full, both halves of it. We already agreed that film coordinates can't be assigned by hand. They're tuned from data. But the second half of the idea says exactly the same thing about the function. The function over the vectors can't be assigned by hand either. It too is tuned from data. And here's the way I'd put the lesson. Every formula we freeze by hand today is a ceiling. The model will never do better than it. So the task is now clear. Build a summary in which the coefficients themselves, who multiplies whom, and with what weight, are tunable numbers, parameters. And conveniently, we already have an operation perfectly suited for that. A weighted sum with tunable coefficients is exactly a vector multiplied by a matrix, an operation you already know. Let me show you how it plays out here. Set up a row of 9 numbers, one coefficient per position of the root sheet. How much to take from the first coordinate of the early film, how much from the second, how much from each flag. The dot product of this row with the root sheet is one number, a weighted summary of the whole root. Want not one summary but several different ones? Set up several rows, and stacking the rows gives you a matrix, W1. Multiply W1 by X, and you get all the summaries at once. Let's check that our old acquaintances feel at home in this notation. The row 1/3 0, 1/3 0, 1/3 0, 0, 0, 0. That's the average of the 3 films' first coordinates, our averaging as a special case. The flag weighting can be assembled out of rows like this too, a little more cleverly. But there's one respect in which everything just changed, and it's the fundamental one. Before, we assigned the coefficients. Now, all 36 cells of the matrix are parameters, and training will tune them. In those cells may grow an average, or a weighting, or some rule people don't even have a name for, whichever turns out most useful for prediction. We'll take 4 rows, 4 summaries. Why 4? We'll discuss a bit later. For now, just note it's again a number chosen by the developer. And let's check the shapes. A 4x9 matrix times a 9x1 vector gives a 4x1 vector. Good. Now let's compute the first summary in full, on the numbers of the already trained model, jumping ahead as usual. The first row of W1 is 0.5, 0, 0.5, 0, 0, 0, 0.5, 0.5, 0. Dot it with the root sheet. 0.5 times 0.9, that's 0.45, plus 0.5 times 1, 0.5, plus 0.5 times the flag of plus 1, another 0.5, plus 0.5 times 0.5, 0.25. Total, 1.7. And notice what this row is doing. It listens to the first coordinates of the 2 early films and to their flags, and multiplies everything else by 0. It's the summary, how good did the user feel at the start of the route, provided the start lay in the right half of the map. One small but important detail remains to be added to each summary. The detail is this. To each summary, we add one more tunable number, its own for each row. These numbers are called biases. They're collected in a vector B1 of 4 parameters, and the full formula of the first stage becomes W1 times X plus B1. What's it for? Well, a weighted sum is chained tight to its input. The fainter the input, the closer the sum sits to 0. And on a 0 input, it's exactly 0, always. The bias unties the summary's level from the input. Think of it as the summary's baseline, the starting height it begins from, before the input adds its part. By tuning the bias, training can raise a summary, make it easy to switch on, or lower it, making it picky. On our numbers, the first summary was 1.7, its bias is minus 0.5, total 1.2. The other 3 rows have their own biases, minus 0.5, minus 0.4, minus 0.35. And notice something curious, all 4 are negative. All 4 summaries are being pressed down by something. That's no accident, and very soon you'll see exactly why the trained model set the bars this way. But first, an honest question for the construction itself. Are weighted sums even enough for our task? Let's stress test our summary stage with the same twin experiment from before. User 17 gave Titanic a 2, flag minus 0.5. The twin adores Titanic, flag plus 1. So the 2 inputs differ in exactly one place, the 9th position, by plus 1.5. How does any given summary change between these 2 users? Well, its row has some coefficient sitting in the 9th position. Call it W9. So the change in the summary is W9 times 1.5. That's the whole answer. And now notice what's missing from that answer. The film itself. The flag's contribution doesn't depend on whose coordinates are lying nearby in the 5th and 6th positions. Titanic's, the mask's, anyone's. Whether the user fell in love with Titanic or fell in love with the mask, the summary shifts by exactly the same amount. And we need exactly the opposite. Liked Titanic should pull the taste toward the romances. Liked the mask should pull it toward the comedies. The reaction to a flag must depend on the film's coordinates. In the language of arithmetic, that's a coupling of flag and coordinates, something like a product of the two. And a weighted sum adds up the position's contributions independently. Multiplying them together is beyond it by construction. I want to be clear that this is not some minor defect. It's a wall. The rule, if liked, pull toward the film, if not, push away, is inexpressible for a linear summary, in principle. Okay, but maybe we can just stack a second stage of weights on top of the first? Do the math on that. The second matrix multiplies the result of the first, and the product of two matrices can be computed in advance, so the two stages collapse into one equivalent stage. 10 stages? Still one weighted sum. Same wall. So linear operations won't breach this wall, no matter how many of them we stack. We need an element of a different breed, and funnily enough, the humblest one imaginable suffices. A single kink. Meet ReLU. It's a function of one number, and it's built about as simply as a function can be. If the number is negative, replace it with 0. If it's non-negative, pass it through as is. The graph is a straight line with a bend at 0. That's the whole function. And we apply it to each summary after the bias is added. What is this bias? Here's the reframe. The bias now works as a threshold. While the weighted sum hasn't yet climbed over its bar, while their total is still negative, ReLU outputs 0. The summary stays silent. The moment it climbs over, the summary switches on and speaks at full voice. And this, by the way, is the answer to the little mystery from the bias scene. This is why the trained model pressed all 4 summaries down with negative biases. It was setting their trigger thresholds. Now, the promised if on live numbers. The second row of our weights listens to just 2 positions. The fresh film's first coordinate, with weight minus 0.5, and its flag, with weight 1. The threshold is minus 0.5. Run user 17 through it. The fresh film is Titanic. First coordinate minus 0.8, flag minus 0.5. Minus 0.5 times minus 0.8 plus 0.4. Add the flag, minus 0.1. Subtract the threshold, minus 0.6. Below 0, 0. Silence. Now the twin. Same Titanic, flag plus 1. 0.4 plus 1 minus 0.5 plus 0.9. The detector lights up. 0.9! Now read what this row just computed. The fresh film lies in the left half of the map, and the user liked it. Both conditions at once. Film on the right, the first term goes negative and sinks the sum. Flag too low, the second term falls short. And here's the part I find genuinely elegant. The weighted sum still multiplies nothing, but the threshold made its answer depend on the combination of the terms, because to clear the bar, they have to add up. That is exactly the conditionality the linear summary couldn't express. The kink is the breach in the wall. So, 1 row, 1 tunable detector of 1 condition. 4 rows, 4 detectors. Let's now gather their readings together and see what we've actually got. Let's finish computing all 4 detectors on user 17's route. The first, the start of the route felt good and it happened in the right half of the map, we already know, 1.2. The second, fresh film on the left and liked, is silent, 0. The third row listens to the same positions as the second, but takes the flag with weight minus 1. So it's the detector, fresh film on the left, and disliked. Compute it. Plus 0.4, plus 0.5, minus the threshold of 0.4, that's 0.5. It lights up, and rightly so. Our user has indeed just been let down by a film from the left district. The fourth detector listens to a mix of the early film's coordinates and flags. The sum comes out 0.7. It lights up too. But what does it mean? Honestly, you can't put it into words. Its set of weights doesn't assemble into any human phrase. And I want to flag that this is how it should be. Nobody hands out captions to detectors. Training picks the weights for their usefulness to prediction, not for readability. Some detectors will simply remain untranslated. So the stage's result is a vector of 4 numbers, 1.2, 0, 0.5, 0.7. It's called the hidden vector. Hidden because it's visible neither at the input nor at the output. It's an internal, intermediate result. And in the language of our imagery, it's the taste point, the place where the user is right now, not on the movie map, but in the sense of state, what he wants, encoded in 4 numbers. Let me draw the boundary of that image carefully so the map doesn't deceive us. The taste point does not live on the movie map. It has 4 coordinates, not 2. It's a separate sheet of the atlas, the taste map, whose axes are our 4 detectors. By the way, notice all 4 coordinates are non-negative. ReLU clipped the minuses, so the taste point always lives in the non-negative corner of its sheet. Taste is encoded by which detectors fired and how strongly. Now, should we be worried that ReLU erases the minuses? Within a single summary, yes, something is genuinely lost. All the negative values merged into one indistinguishable zero. But there are 4 summaries, and each listens to the root in its own way. What got zeroed in one will echo in the others. The loss inside a single coordinate is the price of conditionality, and tuning will itself arrange the weight so that the things that matter don't get lost. And right away, the honest question, because it's begging to be asked. What makes us think these 4 numbers are a portrait of taste and not garbage? At the start, with random parameters, garbage is exactly what they are. Here's the real answer. What will make them a portrait is tuning against the log, and not by anyone's decree, but out of necessity. The taste point is the only thing passed from the root stage to the film choosing stage. It's the bottleneck of the whole construction. Everything that helps guess continuations will have to get packed into these 4 numbers, otherwise the predictions won't improve. So, portrait of taste is a description of the role this vector is destined to play, not a property it was given in advance. The number of detectors, 4, was our choice, by the way. It's a hyperparameter, just like the number of map axes. More detectors, a richer vocabulary of conditions, but costlier and hungrier for data. And the construction we have just assembled, piece by piece, deserves its proper name. And it's a name you have definitely heard. Pause number 2. When the model first drew the network, it drew this. 3 boxes, 2 arrows, which is exactly the picture from every textbook, and exactly the thing this film promised not to do. My own, let's say, 300 moment in my own film. Come on. So the request was blunt. Redraw it so I can count the parameters. W1, 4 rows by 9 columns. It's 4 biases. W2, 6 by 4, 6 more biases. 82 cells total, and every one of them is a real number you can point at. The next scenes run on that version. When the network finally assembles itself, you will see every matrix in it. The stage, multiply by a weight matrix, add the biases, apply ReLU, is called a layer. Ours is called a hidden layer because its result, the taste point, isn't visible from outside. It's an internal variable between input and output. It's also called fully connected. Every summary is connected to every input position. Its row has a coefficient for all 9 positions, no exceptions. And a chain of such stages is called a neural network. The name is historical. A weighted sum with a threshold vaguely resembles how a nerve cell gathers its neighbor's signals and fires when a threshold is reached. But I want this to land. There is no mysticism behind the word neural. You have just built a neural network with your own hands and recomputed it on paper. And now look back at why we needed each piece. The whole answer is sitting in plain sight. The table of continuations didn't generalize. A trillion triples, no data. The cure, embeddings. Films became points on a shared map, and experience began to transfer between neighbors. But a map by itself is not yet a prediction. 3 points and 3 flags have to be condemned into a digest, and any summary fixed by a human hand is a ceiling. The cure, tunable weights. The way of summarizing itself became parameters, and then the weighted sums lacked the conditionality of if liked, then, and that came from the ReLU kink, which turned summaries into detectors. So a neural network is all 3 cures assembled into one construction, a tunable representation plus tunable rules plus nonlinearity. And notice one more thing, because it closes a loop we opened long ago. The coordinates in E and the weights in W1 are parts of one chain, and they will be tuned by one mechanism simultaneously. The map will adapt to the detectors to the map. That is exactly the joint tuning of representation and function that Bengio's idea was about. So the taste point is computed, but the task demands something else, chances, for every film in the catalog. Time to come down from the taste map back to the films and compare the taste point with each candidate. Where we stand, the taste point is 4 numbers. There are 6 candidates. We need 1 score per candidate. How much does this film resonate with this taste? And we already have the mechanism for exactly this, a tunable row of coefficients. So, give every film in the catalog its own row of 4 numbers, 4, to match the number of axes of the taste map. We'll call it the film's landmark. As always, only a name. Behind it is a row of a matrix. The landmark says which detector profile the film answers to, a large number on the first axis, a film for those whose first detector is lit, a negative number on the third, a film against those whose third is lit. A film's score is then the dot product of its landmark with the taste point plus the film's own bias. The same weights plus baseline arrangement as in the hidden layer, nothing new. The 6 rows stack into a matrix W2 of size 6 by 4, the 6 biases into a vector B2. All 30 numbers are parameters. And one multiplication, W2 times H plus B2, produces all 6 scores at once. That's the quiet power of matrix notation. Comparison with the whole catalog is a single operation. Let's compute Alien's score in full, no skipping. Its landmark is 1.0, 0.2, 0.8, 0.5. Bias 0. Dot with the taste point. 1.0 times 1.2, 1.2. 0.2 times 0, 0. 0.8 times 0.5, 0.4. 0.5 times 0.7, 0.35. Sum, 1.95. The rest are computed exactly the same way, so here's the whole column. The matrix, 1.6, Terminator, 1.8, Alien, 1.95, Titanic, minus 0.88, Notting Hill, minus 1.22, The Mask, 0.48. And it reads sensibly, Alien in the lead, unwatched sci-fi. The romance is deep in the negative. The fresh flag on Titanic worked against them through the third detector. 2 footnotes while we're here. In the literature, these raw scores, not yet turned into chances, are called logits. When you meet that word in the wild, know that it means our scores. And a film's bias is an addition independent of taste. Jumping ahead, training will, on its own, push it into the role of baseline popularity. For hits it will grow, for obscure films it will sink below 0. Why that happens, we'll actually see in the training part. But hold on. We agreed to measure closeness with distance, and here suddenly, a dot product. That's not a slip, and the difference deserves to be spelled out. Distance answers the question, do 2 points coincide? For the movie map, that's exactly the right question. Alien and the Matrix are similar if they stand close together. But a candidate's score answers a different question. How much does this film resonate with the current taste? And in that question, 2 things matter that distance simply cannot see. The first is direction. The taste point is a profile of fire detectors. For our user, the first burns bright, the third and fourth less so. A resonant film is one whose landmark is large on the same axes, and the dot product grows precisely when large coordinates fall on large coordinates of the same sign. The second is loudness. Double the landmark's length while keeping its direction. All its scores double. The film answers the same tastes, but louder. So training gains a separate knob. Lengthen the landmarks of films worth offering often and confidently, shorten the ones needed rarely. Distance gives you no such knob. It has no notion of the same profile but louder, only farther and closer. And there's the bonus we've already cashed in, the dot products with all the candidates at once. That's one matrix times vector multiplication. The entire catalog compared in a single operation. So the 2 measures have settled into their proper roles. Distance lives on the movie map and measures how similar films are to each other. The dot product lives on the taste map and measures how much a candidate resonates with a taste. By the way, did you notice something odd along the way? Every film now has 2 vectors, a point on one map and a landmark on the other. That deserves a conversation of its own. So in our model, Alien has 2 vectors. On the movie map, the point 0.8, 1.0, its input embedding, a row of the matrix E, 2 numbers. On the taste map, the landmark 1.0, 0.2, 0.8, 0.5. A row of the matrix W2, 4 numbers. And a fair question, isn't it a mistake to describe one film twice, and with vectors of different lengths at that? It's not a mistake, and here's the way to see it. The film holds 2 different jobs. When Alien appears in a user's history, it's part of the input. Its coordinates say what the person watched, and they get glued into the root sheet. When Alien is a candidate for the next view, that's a different role. Its landmark says which detector profile it resonates with. Different roles, different demands on the vectors, and training will tune each one for its own job. As for the lengths, the 2 vectors just live on different sheets of the atlas. The input on the movie map with its 2 axes, the landmark on the taste map with its 4. Could we have gotten away with a single vector, make the taste point 2-dimensional, and compare it directly with the points of the movie map? Technically, yes. You'd get a different, more rigid construction, where one representation has to serve both roles at once. Ours is more flexible. Each vector is tuned for its own job. Only one thing here is genuinely rigid. The landmark must be the same length as the taste point, 4 numbers against 4. Otherwise, their dot product simply isn't defined. One usage note. When people say the film's embedding without qualification, say to find similar films, or to reuse the vectors in another task, they usually mean the input one, the row of E. We'll follow that custom. Okay, back to our scores. 1.6, 1.8, 1.95, minus 0.88, minus 1.22, 0.48. The ranking of the candidates is already visible, but we promised chances, not scores. To turn one into the other, we'll need a new function. Let's meet it properly. The tool is called the exponential. exp of t is the number e, roughly 2.718, raised to the power t. And here's some altitude control for you. The value of e itself doesn't matter to us at all. What matters are 3 properties of this function. 3, so let me count them out. Property 1, the exponential is always strictly positive. Raise e to the minus 100th power, the minus millionth. You get a small but positive number. 0 or a minus, never. Remember this one. Property 2, it increases. Bigger exponent, bigger result. The exponential preserves the order of the numbers you feed it. Property 3, it grows fast. An addition to the exponent multiplies the result. Plus 0.2 in the exponent, about 1.22 times bigger. Plus 2, 7.4 times bigger. So modest differences turn into multiple fold gaps. Let's run our 6 scores through it. 1.6 gives 4.95. 1.8, 6.05. 1.95, 7.03. Minus 0.88, 0.41. Notice, a negative score became a positive number, just as promised. Minus 1.22, 0.30. And 0.48, 1.62. So, 6 positive numbers, order preserved, and the leaders have pulled ahead. Now, the conversion into chances itself. Remember what we promised. Chances, 6 non-negative numbers summing to 1, because exactly 1 film of the catalog will be next, and the candidates are sharing a single whole. Sets of numbers like this have a standard name, probabilities. From here on, chances and probabilities are synonyms for us. And the conversion is done with the Softmax function, which is almost embarrassingly simple. Pass each score through the exponential, then divide each exponential by the sum of them all. The sum of our 6 exponentials is 20.36. Divide each one by it. The matrix, 0.24, Terminator, 0.30, Alien, 0.35, Titanic, 0.02, Notting Hill, 0.01, The Mask, 0.08. And they sum to 1 automatically. The numerators are exactly the terms of the denominator. Read it out loud. The model gives Alien 35 chances out of 100, and the romances 1 or 2 apiece. Now, why this dance with exponentials? Why not something simpler, like dividing the scores themselves by their sum? Well, scores can be negative. Titanic would get a negative chance, and the sum of the scores could even come out to 0. Division by 0, the whole thing collapses. The exponential cures both ills with property 1, and with property 2 it preserves the order. Bigger score, bigger chance. Property 3 pulls its weight too. The fast growth sharpens the differences. The favorite pulls away, the hopeless get pressed towards 0. But, and this matters, not to 0 exactly. The exponential is strictly positive, so every chance is strictly between 0 and 1. The model is never absolutely certain. Remember that. It will come in very handy when we measure error. The name Softmax, a soft maximum, comes from exactly this behavior. The function almost picks the maximum, handing the favorite the lion's share, but softly, without zeroing out the rest. And when the scores change a little, the shares change smoothly. One practical footnote. The exponential of very large scores would overflow a computer, so in practice, the largest score is subtracted from all of them before exponentiating. The fraction doesn't change. The common factor cancels in numerator and denominator. And with that, the whole prediction path is assembled. Log, coordinates, root sheet, taste point, scores, chances. But notice that every number inside has been jumping ahead, borrowed from the snapshot of a trained model. Time to keep the main promise of this film, to show where those numbers come from. On to training. To tune parameters, we need problems with known answers. And the log is full of them. After all, it recorded not only what people watched, but what they watched next. The slicing is simple. Slide a window of 4 consecutive views along each user's history. The first 3, with their ratings, are the input. The 4th film is the correct answer. Shift the window by 1 view. That's the next example. And so on, down the whole history. Now, user 17's history did in fact continue. After Titanic, he watched Alien and rated it 5, and then The Mask, rated 3. So let's slice it. Example 1. Input. The Matrix 5, Terminator 4, Titanic 2. Correct answer, Alien. And look at that. Our running example was a training example all along. The model was predicting Alien, and the user really did watch Alien. Example 2. Input: Terminator 4, Titanic 2, Alien 5. Answer: The Mask. 2 clarifications. The correct answer is a film's number, a fact from the log. We'll call it C star. The rating the user gave that fourth film plays no part in the example. We predict only which film, remember? And second, whose example it is doesn't matter. The model knows nothing about users. Every example stands entirely on its own. From a log with millions of views, millions of examples get sliced. So now the model can answer on every example, output its chances. But to tune the parameters, we need to be able to say how bad an answer is, and say it with a single number. For that measure, we'll need one more function, the exponential's own sister. Pause 3, the logarithm. This one is my favorite fix in the whole project. The first draft of this part said, the loss is minus the logarithm of the probability, and moved on. And that's the, let's say, 300 disease again. You cannot answer why the logarithm with because logarithm. And the fix wasn't a better paragraph. It was a rule written into the prompt itself. Every new concept must arrive in 4 beats. Try the naive thing first. Watch it break on the same numbers. Bring the concept in as the repair, then check it did repair. The logarithm is the first concept told this way, and here's the part I didn't expect. The model then reused the pattern on its own. For the loss, for derivatives, for the chain rule, for backpropagation. Watch the next scenes with that rhythm in mind. The natural logarithm is the function inverse to the exponential. Take a number, run it through the exponential, run the result through the logarithm, you get your number back. The exponential answers what comes out of this exponent. The logarithm answers what exponent produced this number. What interests us is how it behaves on chances, numbers between 0 and 1. The logarithm of 1 is 0. Now heading down, the logarithm of 0.5 is about minus 0.69, of 0.345, minus 1.06, of 100th, minus 4.6, of 1000th, minus 6.9. The closer the argument creeps to 0, the deeper the logarithm plunges into the minus, and the plunge has no bottom. At 0 itself, minus infinity. And notice the character of this function, because it's about to matter a lot. Between chance 0.5 and chance 1, the difference in logarithm is modest, less than 1. But between 100th and 1000th, a full 2.3. Even though by ordinary subtraction those two chances are nearly indistinguishable, both tiny. So the logarithm sharpens differences precisely near 0, down among the almost hopeless chances. Keep that property in mind. It's about to become the main character. Here's the measure. Look at the chance the model gave the correct film. Just that one number. Take its logarithm and flip the sign. The loss? L equals minus the natural log of the correct film's chance. In our example, the correct answer is Alien. Its chance, without the rounding we did for neatness in the Softmax scene, is 0.345. So the loss is minus the logarithm of 0.345, about 1.06. Let's check the measure behaves the way a measure of how bad should. Had the model given Alien a chance of 1, loss 0, the ideal, unreachable by the way, we saw that chances sit strictly below 1. Chance 0.5, loss 0.69. Chance 100th, 4.6. Nearly wrote the answer off, enormous loss. So, smaller loss, bigger chance for the correct answer. To reduce the loss is precisely to improve the predictions. Now, why the logarithm and not something simpler, say 1 minus the chance? Because of exactly that character we noted last scene. For the measure 1 minus the chance, the errors 100th and 1000th are almost the same, both about 1. For the logarithmic measure, the second is noticeably worse, 6.9 versus 4.6. The logarithm is merciless to confident errors, the cases where the model has all but ruled out the correct answer. And those are exactly the cases most important to fix. There's also a second reason, which I'll leave on credit for now. For the pair sovdap plus logarithm, the corrections to the parameters will come out as an astonishingly simple formula. You'll see it for yourself in a few scenes. One more thing worth noticing. We penalize only the correct film's chance. There's no separate penalty for the wrong ones. And none is needed. The chances are linked, their sum is always 1, so the only way to raise the correct one is to take share away from the wrong ones. Pushing one chance up automatically pushes the rest down, so now every example has a number for how bad. Next, let's state what training actually does, and be a little surprised at what a simple-looking task it turns out to be. Let's count everything the model is allowed to tune. The Atlas E, 6 rows of 2 numbers, 12. The hidden layer weights, 4 rows of 9, 36, plus 4 biases. The landmarks, 6 rows of 4, 24, plus 6 biases. 82 numbers in all. In a real model, there will be millions, but that changes nothing essential. What's in front of us is a control panel with 82 knobs, and above the panel, a single readout, the average loss over all training examples. Add up the losses, divide by the number of examples. Why the average, and not the loss of some one example? Because there is one model for everyone. One set of parameters has to answer well on the first example, and the second, and the millionth. The average is exactly the number for how bad overall. And now the training task itself in one sentence. Find the position of all 82 knobs at which the number on the readout is as small as possible. That's the entire formulation. Notice what's not in it. No genres, no understanding of films, only knobs and a readout. By the way, where do the knobs stand right now, before the first tuning step? Same story as the coordinates on the gray starting map. All the weights are filled with small random numbers. Different rows need different seeds, and nothing should shout by sheer size. The biases can start at zeros. The randomness of the weights already makes all the summaries different. Now mentally turn any knob, say Titanic's second coordinate, or the third detector's threshold, and the number on the readout changes. Every single one of the 82 numbers takes part in computing the loss. But the knobs are all linked through a shared chain. Turn one, and the taste points of every example where Titanic appeared have changed, and the scores, and the chances. How do you even approach a task like that? Let's start with the most honest way, the one that would occur first to any of us. Method 1, the honest one. Turn a knob and watch what happens. For simplicity, let's take not the average loss, but the loss of our first example. The readout shows 1.0637. From now on, we're watching the 4th decimal place. Experiment 1, the knob, the mask's bias, currently 0.3. Turn it up by 100th, 0.31. Recompute the whole chain, the mask's score has grown. Softmax redistributed the chances, Alien's chance sagged a little. The readout, 1.0645. So the loss rose by 8/10,000ths. 2 takeaways immediately. First, this knob must not go up. It should be turned down. And second, a genuinely valuable number, the ratio, the change in the loss divided by the change in the knob. 8/10,000ths over 100th plus 0.08. Let's hold on to that. Experiment 2, Alien's bias, from 0 up by 100th. The readout, 1.0572. The loss fell by 65/10,000ths. The ratio, minus 0.65. So this knob turns in a useful direction and it's 8 times more influential. Which makes sense if you think about it. Alien is the correct answer. Raising its score is direct profit. Experiment 3, Notting Hill's first coordinate on the map. Turn it, and the readout doesn't budge. 0. Also understandable, Notting Hill wasn't among the 3 films watched. Its coordinates simply weren't part of this example's computation. Now look at how much the wiggling gave us. For every knob, a sign, which way to turn, and a number, how influential it is. So turn every knob a little against its ratio, and the loss moves down. Repeat, down again. Sounds like a plan for training. But before we celebrate, let's count what this plan costs. To learn the ratio of one knob, we reran the entire chain. There are 82 knobs, so one single tuning step costs 83 full passes, 1 baseline plus 1 per knob. For our toy, trivial. Now the real scale. Millions of knobs, millions of passes for a single step. And the steps, as we'll see, are needed in the millions too, because each one shifts the knobs only a little. Millions multiplied by millions. No computer can pay that bill. And here's the galling part. Almost all of that work is duplicated. We wiggle the mask's bias and recompute the entire root sheet, the entire taste point, which didn't change. The knob sits right at the output. We wiggle a coordinate of the matrix and rerun all 6 exponentials. Different knobs share one and the same path to the readout, and we're paying for that path anew for each of them every time. So the task has sharpened nicely. We need those same ratios, the sign and strength of each knob's influence, but obtained not by millions of passes, by calculation. The good news, such a calculation exists, and it costs roughly 1 pass. There is no bad news. But before we build it, let's give the quantity we're measuring a precise name. It has earned one. The ratio from our experiments has one subtlety. It depends slightly on the size of the wiggle. Wiggle the mask's bias not by 100th, but by 1/10. The ratio comes out 0.083. By 100th, 0.080. By 1,000th, 0.0794. And from there on down, even at 1,000,000th, the same 0.0794. As the wiggles shrink, the ratio stops changing. It settles. And that settled value is called the derivative of the loss with respect to the parameter. The notation reads dL by d theta, the change in L per unit change of the parameter theta at tiny changes. The word is new, the content is not. The derivative is exactly what we were measuring by wiggling, just carried to the limit of care. And it reads exactly the same way. Derivative positive. Increasing the parameter increases the loss. Turn it down. Negative, turn it up. 0. The parameter has no influence here at all. And the magnitude is the strength of the influence. A derivative of minus 0.65 means every 100th of a turn upward takes about 65 10,000ths off the loss. One refinement to the name, in full it's called a partial derivative, from part. One parameter wiggles while the other 81 stay frozen in place. Each knob gets its own partial derivative, with all the others held still. So at every moment, each of the 82 knobs has its own little hint number. Let's give a name to the whole collection at once. Collect the partial derivatives of all 82 knobs into one vector, one number per knob in a fixed order. This vector is called the gradient, and I want to deflate the word immediately. There is nothing new inside it. It's simply all our hints stacked into a column, plus 0.08 for the mask's bias, minus 0.65 for alien's bias, 0 for Notting Hill's first coordinate, and so on through all 82 numbers. Two properties of the gradient are worth saying out loud. First, it's tied to the moment. These are the hints at the current position of the knobs. Turn the knobs, and the chain of computation changes, and all the derivatives have to be obtained anew. A gradient is not issued once and for all. Second, it's tied to the example. The loss of the first example has one gradient, the loss of the second, another, and the average loss has their average, since the derivative of a sum is the sum of the derivatives. And now all the words are in place. The tuning rule we've been heading toward this whole time can be spoken in a single line. Here's the rule. Shift every knob against its derivative by an amount proportional to the derivative. As a formula, theta is replaced by theta, minus eta times dl by d theta. The minus sign is the heart of the rule. The derivative shows where the loss grows, so we go the opposite way. And notice how much comes along for free. Influential knobs get a bigger shift, weak ones a smaller one, uninvolved ones none at all. All of it follows on its own from the derivative's magnitude. The number eta is called the learning rate, a small positive multiplier, the length of the step. In our teaching example, we'll take eta equal to 0.1. Coarse but visible. The mask's bias shifts from 0.30 to 0.292. Alien's bias grows from 0 to 0.065. The loss on the readout goes down. And that right there is one step of what's called gradient descent. Descent because it goes down the loss. Why must the step be small? Remember where the derivative came from tiny wiggles. It's a local hint, honest near the current position of the knobs. Over a large turn, the chain reorganizes itself, and the old hint can lead you to a place where the loss is higher. Make eta big, training jumps around and falls apart. Make it tiny, everything is correct but at a snail's pace. Real values are on the order of thousandths, and they're not derived from theory, they're found by trial. It's a hyperparameter. And this smallness is also why so many steps are needed. Each step is a little one, and the map gets created by the accumulation of millions of small shifts. So the rule is in place. What remains is the cost. So far, we can obtain the hints only by wiggling, one pass per knob. Time to keep the promise from the price of naivety scene. Learn to compute all the derivatives at once, almost for free. And the key is one simple observation about chains. Here's the observation. Suppose the knob theta doesn't act on the readout directly. It turns an intermediate gear U, and that gear turns the readout. Wiggle it, theta by 1/100th, U moved by 2/100ths. So the first link transmits 1 to 2. And suppose we also know that when U shifts by 2/100ths, the readout changes by 6/100ths. The second link transmits 1 to 3. Then the whole path, 100th at the input, 6/100ths on the readout, a ratio of 6. And 6 is 2 times 3, the link sensitivities multiplied. Which makes sense if you think it through. The first link doubles the wiggle, the second triples the result of the first, together, sixfold. This is what's called the chain rule. The derivative with respect to a distant knob equals the product of the link's derivatives along the path. And one addition, if the knob has two paths to the readout, say it turns both U and V, and both of those turn the readout, then the path's contributions add up. Each path carries its influence independently, and tiny changes add. Now look at our model through these eyes. A coordinate of the matrix doesn't touch the loss directly. It sits in the root sheet. The root sheet influences the summaries, the taste point, the scores, the chances, the loss. A long chain, yes. But every individual link in it is simple. Multiplication by a known coefficient, an addition, a ReLU, a Softmax. And if you know the local derivative of each link, the distant ones assemble themselves by multiplying and adding, without a single wiggle, by pure calculation. All that remains is to organize this calculation so that nothing gets computed twice, and the order in which that's done has a name of its own, one of the most famous names in all of machine learning. Let's meet it. Last pause, and it's the big one. Backpropagation. The first version of this scene was 6 steps long, an abstract chain, x to h to z to p to the loss, and one sentence. The error flows backwards. Sure, I believed it. I just couldn't see it. And trust me is not an explanation. So, one more request. This model has 82 numbers. Show me the error wave reaching every single one of them. The scene grew from 6 steps to 12. Value cells on top, blue parameter grids below, and a purple wave that fills a counter as it goes. 30 of 82. 70. 82 of 82. It became the densest scene of the whole film, and honestly, it was worth every pixel. Here it is, uncut. Look at the paths from different knobs to the readout. They merge. The matrix's coordinates, the detector's weights, the landmarks, all of them pass through the same final links, the chances, the loss. And with wiggling, we paid for those shared segments anew for every knob. That's where all the waste was hiding. So here's the solution. Go from the end. First, compute the readout sensitivity to the chances. That's the first link from the edge, and its derivative is simple. From it, the sensitivity to the scores, one application of the chain rule. And since the scores depend on the landmarks and biases directly, right there along the way, the derivatives for all the cells of W2 and B2 just drop out. Then further back, the sensitivity to the taste point, from it, to the summaries, and along the way, the derivatives for W1 and B1. And finally, to the root sheet, and therefore to the used rows of the Atlas E. One pass from right to left, and the derivatives for all 82 knobs are in hand. Why does the economics work? Because the sensitivity of each node gets computed once, and then reused by every knob whose path runs through that node. No influence is paid for twice. And the result is honestly astonishing. The full gradient costs roughly as much computation as one forward pass of the model. Not 83 passes, 2, forward and back. And for millions of knobs, the same 2. The algorithm is called backpropagation. The error propagates from the readout backward along the chain, all the way out to the most distant knobs. Now, you will never have to write out the link's derivatives by hand. Software libraries record the chain of computations and walk it backward automatically. But what is worth seeing with your own eyes at least once is exactly which hints this wave delivers to our knobs. Let's start with the scores. There's a formula of rare beauty waiting for us there. The wave has reached the scores, and here's what the derivatives turn out to be. The derivative of the loss with respect to a film's score equals its chance minus 1, if the film is the correct one, and simply its chance if it is not. Compactly, this gets written with the correct answer vector y, a 1 at the correct film's position, zeros elsewhere. And then the derivative with respect to all the scores at once is p minus y. That's it. That's the formula. And it's not a postulate. It comes out of applying the chain rule to the softmax and logarithm links. We'll skip the derivation, but we can verify it. In fact, we already have. Look, a film's bias adds into its score directly, so the derivative with respect to the bias coincides with the derivative with respect to the score. For the mask, the formula says chance 0.08, a nudge of plus 0.08. And what did we measure by wiggling back in experiment 1? Plus 0.08. For alien, the formula says chance 0.345 minus 1 minus 0.655. Measured minus 0.65. The formula matched the experiment to the precision of our measurement. I love this check. Now let's read the formula for meaning because it deserves it. The correct film gets a nudge upward. The stronger, the smaller its chance was. Underrated? Receive a bigger correction. Every wrong film gets a nudge downward, proportional to its chance. A candidate the model wrongly believed in gets pushed down hard, while one it never gave a chance to is barely touched. Confidently wrong. Pay dearly. Notice, the very mercilessness toward confident errors that we built in with the logarithm has come back out the other side in the form of corrections. And from here you can already see the path of the biases. A film's bias catches the same nudges as its score. So a film that often turns out to be the correct answer, across all sorts of histories, accumulates upward nudges and grows into a baseline popularity. A rare guest sinks into the minus. The promise from the landmark scene, kept. But the score nudges are only the end of the path. Now let's trace how the wave rolls all the way to the farthest frontier, to the coordinates on the map. Let's take the farthest knob of all, the matrix's first coordinate, 0.9, and assemble its derivative by hand. Once in our lives. Along the chain, link by link, from the readout backward. Link 1. How does the loss depend on the taste point? The taste point acts on the loss through all 6 scores at once, 6 paths, and the contributions add. Along each path, the scores nudge times the coefficient with which the first axis enters that score. And those coefficients are the first numbers of the landmarks. Compute 0.24 times 0.8 plus 0.3 times 0.9 minus 0.655 times 1, then small change from Titanic, Notting Hill, The Mask. The total, about minus 0.21. And the meaning here is completely transparent. Alien pulls hardest of all. The correct answer is saying, first axis of taste, grow. Link 2. How does the taste point depend on our coordinate? The coordinate sits in the first position of the root sheet. It enters detector 1 with coefficient 0.5, and that detector is on. ReLU lets the influence through. Multiply. Minus 0.21 times 0.5, about minus 1/10. There's a second path too. It enters detector 4, also with coefficient 0.5. The loss's sensitivity to the fourth axis is tiny, about plus 1/100th. Contribution, plus 6/1000ths. And the path through detector 2? Blocked. On this example, that detector is off, outputting 0, and under tiny wiggles it would keep outputting 0. A switched-off link conducts nothing. One small side agreement in the margins: if a detector's sum lands exactly on its threshold, the slope right at the kink is formally undefined. In practice, it's taken to be 0 by convention, and landing exactly on the kink is vanishingly rare anyway. Add up the paths, about minus 1/10. Link 3, the step itself. 0.9 minus the teaching learning rate of 0.1 times minus 1/10, 0.91. The matrix's point moved 1/100th to the right, microscopic. But look where? Toward where detector 1 burns brighter, which means aliens' score on histories like this one will rise. The example nudged the map toward itself, by a hair. And notice what just happened. The phrase, training moves the points, has turned from imagery into a calculation you've now done by hand. It remains to find out exactly whom each example moves, and there's a surprise waiting there. So, over one example, who moved? On the movie map, exactly 3 points. The Matrix, Terminator, Titanic. Their coordinates were in the route sheet. The wave reached them. The other rows of the atlas took no part in the computation. The loss doesn't depend on them. Their derivatives are honest zeros. We even measured that, remember? The Notting Hill experiment, where the readout didn't budge. And now the unexpected part. Alien's point didn't move either. Yes, it's the correct answer. But its coordinates weren't part of this example. The input consisted of other films. So the rule is, a film's point moves if and only if the film is among those watched. On the taste map, though, the movement is massive. All 6 landmarks and all 6 biases received corrections. And the reason is sitting right in the nudge formula. Every film's P minus Y nudge is non-zero. Every score stood in the Softmax denominator. Every one of them is a little bit guilty or a little bit right. Alien's landmark gets pulled toward the taste point, so their dot product grows. The landmarks of the overrated Terminator and the Matrix get pushed away from it, and the biases catch their own nudges. Remember this asymmetry. It's worth keeping. A film's row in the atlas learns only from the histories where the film was watched. Its landmark learns from every example in the catalog. And a small aside, if a film repeated within the triple, both of its positions send nudges into the same atlas row. It receives the sum of two opinions. The two vectors of one film live genuinely different learning lives, each according to its role. All of this is the nudging from one single example. But an example is a noisy advisor. It pulls the map toward itself, personally. The next step is to learn to listen to examples in chorus. In practice, a step is taken not on one example, but on a bundle of them, called a mini-batch. Take our bundle of two. The first example with the answer alien, the second with the answer, the mask. The losses of both get averaged. The batch's loss is their half sum. And since the derivative of an average is the average of the derivatives, each knob's correction is the average of its corrections over the batch's examples. Watch how this plays out on Titanic's row. It was watched in both examples, so its point receives two nudges, one from each, and moves by their average. A compromise of two opinions. The matrix appears only in the first example. From the second, it gets zero contribution, so its nudge is halved in the average. And the landmarks, as we know, receive nudges from every example. For them, the averaging is especially welcome. Why average at all? Because one example is a noisy advisor. It demands the map be fitted to it personally. A batch advises more calmly. The random whims of individual examples cancel each other out, and the shared tendencies add up. There's a bonus, too. The computations for all the examples of a batch run simultaneously, faster than running them one by one. The batch size is again a hyperparameter. In reality, dozens or hundreds of examples. R2 is a teaching minimum. And just in case the terms are starting to blur, the batch size has nothing to do with the number of detectors or map axes. It's a knob of the training procedure, not of the model's design. Batch after batch, step after step, that is how training goes. But before we run this machine at full speed, one precaution is needed. Without it, the whole enterprise can quietly fail, in a way we wouldn't even notice. The model has 82 knobs, a real one has millions. And that much storage capacity hides a danger. Instead of learning regularities, after sci-fi you liked, you watch sci-fi. The model may simply fit the numbers to the specific training examples, like a student who memorized the answer key without understanding a thing. This phenomenon is called overfitting. And here's what makes it treacherous. From the outside, cramming is indistinguishable from understanding, as long as the problems are familiar. On the training examples, the loss falls. The predictions look brilliant. There is exactly one way to tell the two apart: new problems. So before training begins, part of the examples, say a tenth, gets locked away in a safe. Training has never shown them at all. They're picked at random, and preferably whole users at a time. All of a held-out user's examples go into the safe together, so training can't peek at his history even out of the corner of its eye through neighboring windows of the slicing. From then on, you watch two readouts at once. The loss on the training examples will fall almost always. We're pushing it down directly, no news there. The truth lives on the second readout, the loss on the held-out examples. While the model is learning genuine regularities, both fall. The regularities are shared. They help on new histories too. But if the training loss keeps falling while the held-out one turns upward, that's the signature. The model has switched to cramming, fitting the numbers to what it has seen at the expense of the new. So the exam is ready. Now training can be launched for real, and we can agree on when to stop it. One complete pass through all the training examples is called an epoch. Before each epoch, the deck of examples gets reshuffled, so that consecutive histories of one user don't clump into batches, and the batch's advice stays diverse. Then it's cut into batches, and off we go. Batch, step, step. And one epoch isn't enough. The steps are tiny, and by the end of the pass, the parameters are no longer what they were at the start. So the same examples have something new to say from the new state. Training runs several epochs, sometimes dozens. The examples flow through the model again and again, each time shifting the knobs a little. When to stop? Watch the held-out readout. The typical picture goes like this. Both losses fall at first. The model is grasping the regularities. Then the held-out one flattens out and starts creeping up, while the training one keeps falling. The shift to cramming has begun. We stop at the held-out minimum. Beyond that point, the model doesn't get smarter. It memorizes. Now, a fair worry. Can a step on one batch spoil the answers on other examples? It can. There are no guarantees for any individual step, but the steps are tiny, the batches alternate, and the demands of most batches don't contradict one another. The regularities are shared. Contradictory demands drag the knobs this way and that, and balance out as they accumulate. Averaged over many steps, the average loss creeps downward, and that is exactly the thing we're monitoring on the second readout. One more pitfall of the procedure deserves saying out loud. Gradient descent carries no guarantee that millions of steps will arrive at the best of all possible knob settings. In theory, you can get stuck in a place where every small step hurts, even though something better exists far away. Practice, however, is surprisingly robust. With a huge number of parameters, there are many directions for maneuver. The batch noise helps climb out of small pits, and the final judge is not theory anyway. It's that same held-out readout. If the quality is acceptable, the model will do. So the mechanics of training are fully assembled, which leaves the main question of the whole film, the one we actually came here for. Why does this mechanics turn a random gray cloud into a meaningful map? Follow 2 points with me: the Matrix and Terminator. The log holds thousands of histories where, after the Matrix with a high rating, people watch Alien, and thousands just like them with Terminator. Now, what does each such example do? It nudges the watched film's coordinates toward wherever makes it easier for the detectors to build a taste point that raises Alien's score. The histories are alike, the correct answers coincide, so the directions of the nudges are alike too. And example after example, epoch after epoch, the 2 points drift together. Why? Because it pays for them to stand side by side. Then the same detectors serve both films, and the same landmarks resonate with their histories. The total loss is smaller that way. The coming together is no miracle. It's direct profit for the readout. Now the reverse plot. At the start, the points are scattered at random. So what if Titanic happened to land next to the Matrix? Then the model starts confusing their histories. After Titanic, it reaches for predicting Alien, and it is systematically wrong, because in the log, quite different films follow Titanic. And every error means nudges that drag the culprits apart. It pays the detectors for dissimilar histories to arrive from dissimilar places on the map. The confusion stamps itself out. And a third plot, the most important one for honesty's sake. One and the same film appears in thousands of different histories, and their nudges pull its point in different directions. Does the point thrash about? No, the steps are tiny. It drifts to where the nudges balance out. A compromise position, the best one for all the contexts the film lives in at once. And that is exactly why the final position is so informative. 2 numbers, compressing the entire collective experience viewers have had with this film. Run millions of steps, and the gray cloud separates into layers. Sci-fi drifts toward sci-fi, romances toward romances, the mask finds its own corner. Nobody told the model a single genre. The districts grew out of nothing but coinciding continuations. And the real structure is finer than genres. Films of one era, one mood, one circle of viewers become neighbors, if that's how people actually watch them. One warning though. In our toy city, the first axis looks suspiciously like a sci-fi versus romance scale. That's the luck of a tiny example, not a rule. On real maps with dozens of axes, an individual axis usually doesn't translate into human language at all. The meaning is carried only by the mutual arrangement of the points as a whole. Just as we agreed back when we first met the map. Sounds beautiful. But is it checkable? It is, and very simply. Take the trained map and take the ruler from the distance scene. The Matrix's neighbors? Compute. To Terminator, the root of 0.05, about 0.22. To Alien, the same. To Titanic, 1.7. To Notting Hill, almost 1.8. To The Mask, just under 1.9. And the list speaks for itself. Nearby, sci-fi. Far away, everything else. On real maps, trained on real logs, these lists look exactly this convincing. It's a typical, reproducible result, and it's the best quick test that training has actually succeeded. Now notice what we just did because it's easy to miss. We got a meaningful answer. What is the matrix similar to, without running the prediction model at all? No routes, no detectors, no softmax. Only rows of the atlas and a distance. The learned map is a product in its own right. Those similar films and, because you watched, blocks in service interfaces are built literally like this, a search for the nearest points on a learned map. And the same vectors can be carried off into other tasks entirely, anywhere you need numbers that express how similar films are in viewers' behavior. One note along the way, the embedding itself is not tied to our detectors and landmarks. It's a way of representing things, objects as points of a shared map, and our construction is only one of the buildings you can raise around it. The same atlas rows could feed a completely different model, and the word embedding would mean exactly the same thing. So here is the embedding at full height, a compact numerical description of a film, derived from the collective behavior of viewers, and written down as the position of a point on a shared map. What remains is to see how the trained model actually serves, and to honestly survey the limits of what it can do. Training is stopped, and all 82 numbers get frozen. From this second on, they will never change again. They're saved to a file. The Atlas E, the detector's weights and thresholds, the landmarks and biases, 5 arrays of numbers, plus a short program that performs the chain you now know by heart. Take the Atlas rows, glue the root sheet, compute the detectors, the scores, the chances. And here's a striking accounting. Everything training needed, service does not. No training examples, no derivatives, no learning rate, no epoch counters. All of it can simply be thrown away. A model in production is 5 arrays and a chain of multiplications. That's enough to run it on any server. A good metaphor for this moment. The Atlas has been compiled and it has gone to print. During training, we spent months moving the points. Now it's a printed impression. You navigate by it and nothing gets redrawn. Let's watch one working day of such a model. A request comes in. A user with the history the Matrix, 5, Terminator, 4, Titanic, 2. Sound familiar? We run the chain, exactly the same one as in training, but once, and with none of the tuning machinery. No loss is computed, no derivatives are needed, the parameters are frozen. Out come the chances. 0.24, 0.3, 0.345, 0.02, 0.01, 0.08. A single answer gets picked by the argmax operation, the position of the maximum. Not the largest value itself, but the place where it stands. The maximum is 0.345, position 3, alien. Could 2 chances tie exactly? In real number computation, practically never. If it happened, take either, say the one with the smaller number. And a small observation. Softmax preserves the order of the scores, so for a single answer, we could just as well take the position of the largest score. The chances earn their keep when the service wants to show its degree of confidence, or assemble a shelf. A shelf is top K, the K films with the highest chances, as many as the screen holds. Let's assemble a top 2. First, Alien. Next by chances is Terminator, but it's already been watched, skip. The Matrix, likewise. Take the next one, the Mask. The shelf, Alien and the Mask. Excluding the watched is a technical detail in picking the best. Skip the numbers from the user's history, that's all. And he really did watch Alien, we know that from the log. Of course, one example proves nothing. So how do we measure quality honestly? Here's how it's measured. Take the held out examples, that same safe training never saw. For each one, run the model, assemble a shelf, say a top 10, and check one fact. Did the real next film land in the shelf? The share of hits is the metric. One understandable number. In what percentage of cases did the model's 10 guess right? Now, to judge whether some percentage is a lot or a little, you need a bar to compare against. Random guessing in a catalog of 10,000 films hits with a 10 in one case out of 1,000, 0.1%. Trained models of this design deliver percents and tens of percents, tens to hundreds of times above random. The exact figure depends on the data, but the gap over randomness is precisely the proof that regularities were caught, not dreamed up. And notice how modest the setup is. We don't demand guessing a person's single choice, only that the real choice lands among the 10 offered. For a recommendation service, that's exactly what success means. A good shelf is one people take from. So the model is in service, and the quality is measured. The final honesty is admitting what it cannot do. The first limit is actually a pleasant one. The model stores nothing about specific people, no profiles, no history. The entire profile is the 3 rows of the request, turned on the fly into a taste point. So a new user who didn't exist during training is served from the very first second, as long as there are 3 views. His route gets laid out on the ready-made map, and if there are fewer than 3 views so far, then our construction in its pure form does not apply. There's nothing to fill the input with. The service acts differently for a while, shows what's popular, for instance, until a triple accumulates. The second limit is hard. Dune enters the catalog. After training, there is no point for it on the map, no meaningful row in the atlas, no landmark of its own on the taste map. Either those rows don't exist at all, or they hold untouched starting noise. And both consequences are unpleasant. Dune can't be taken into account in the input, and Dune can't be recommended. It has neither a score nor a chance that deserves any trust. The film exists, but for the model, it doesn't. This is called the cold start problem. And the cure, in essence, is 1. Train the model further, on a log where Dune is already being watched. Then the nudges of training will draw its point onto the map. The asymmetry here is instructive, so let me underline it. For the model, people are routes, assembled on the fly out of ready-made points. Films are the points themselves, and points get placed only by training. One last step remains, to put all the sizes back where they belong, from the teaching screening room to the real one. Let's restore the real sizes. 10,000 films, and each has its 2 vectors, an atlas row and a landmark. The movie map gets 64 axes. A map like that can't be drawn, but notice, not a single formula changes. The vectors are simply longer, and distances and dot products are computed by the same sums as ours, just with more terms. The route sheet, 3 times 64 plus 3 flags, 195 numbers. Detectors, 256, a much richer vocabulary of conditions than our 4. Now recount the control panel. The atlas, 10,000 by 64, 640,000. The detector weights, 256 by 195, 49,920 plus 256 thresholds. The landmarks, 10,000 by 256, 2,560,000 plus 10,000 biases. In total, 3,260,176 tunable numbers. 3.25 million knobs, and not one of them is turned by hand. The same gradient descent, the same p-y nudges, the same backward pass that we worked through by hand on 82. Let's look back from the height of the whole road. The table of continuations died under 1 trillion triples, so we gave every film a place on a shared map, so that experience could transfer between neighbors. Handmade summary formulas turned out to be a ceiling, so we made the rules themselves tunable. Detectors with thresholds, landmarks with baselines. The measure became the loss, the teacher, the log, the mechanics, tiny steps against the derivatives. And millions of nudges turned a random cloud into a city with districts, sci-fi with sci-fi, romances with romances, though the model never once heard the word genre. And at the center of it all, the embedding, a short vector of coordinates, a film's position on a shared map, learned from the collective behavior of viewers. The mutual arrangement of those points is a compressed memory of everything millions of people watched and how they continued. So from now on, when you meet the word embeddings about films, words, products, anything else, you know what stands behind it. Not magic, a map drawn by the data.